Good evening. Today we'll be conducting the problem solving and doubt clearing session for week 11. And I'm Calvin Joseph, and I'll be teaching from this course, the doubt clearing session. So this is the outline for today. First, we will see about how in MATLAB we can do simulation for digital voltage control. Then how the data, which is their hardware waveforms which are displayed on the oscilloscope, how you can get that data in a CSV file, etc., and how it can be used for post processing and for comparing the hardware results with simulation results. We will talk about certain steps regarding that. Then we will also recap how we are doing loop shaping and design, and how we are designing the controller for digital voltage mode control. Next, certain hardware results will be shown, and the load current feed forward part also will be discussed, as well as why we need multi-mode control also. I will briefly touch upon that. Okay, so in the beginning, I'll just be talking about switching frequency. So, Sagar, you're the one who wanted derivations, right? For switching frequency?
No, sir, it is clear.
Well, actually, he wanted, so I just showed to him once. So you consider for constant on time assume. Sure. Suppose this is a waveform of your inductor current. Okay. This is your IL max. This is your IL minimum. Okay. And this is your delta IL. This is your current ripple. This is your rising slope M1. This is your falling slope M2. Okay. This time is your on time. This time is your off time. Okay, this total time is the time period, steady state time period. So I'm discussing about what is a variable frequency. So the effective in steady state. What do you mean the steady state? This IL minimum over here will be same as the IL minimum over here, and the IL max over here will remain as, and this IL max will remain the same because it has reached a steady state operating point. Okay, that is the basic condition. So when it has reached a steady state operating point, the frequency of your variable frequency control will reach one particular frequency. Now, how will we determine that frequency? So now for buck converter, M1 is equal to Vin minus V output upon L, and M2 is equal to V output upon L. So this change delta IL is equal to this M1 into T on. Okay, this delta IL is equal to M1 into T on, and also it should be equal to M2 into T off. Okay, it is also equal to M2 into T off. So let me substitute. So we have Vin minus V output upon L into T on is equal to V output upon L into T off. Okay. So this L and L will get cancelled. So you effectively get Vin minus V output upon L, no, V output into T on is equal to V output into T off. Now I'll take V output to the other side. So I will get Vin into T on is equal to V output into T on plus T off. So we have Vin into T on is equal to V output into T, your entire time period. So you get V in into T on is equal to V output upon your switching frequency. So your switching frequency is equal to V output upon V in into 1 upon T on. Okay. So when your on time is fixed, okay, when your on time is fixed, T on is fixed, how your switching frequency depends on your output voltage and your input voltage. Okay. Shafid, is this clear? Okay. Similarly, if you want to do for off time also, you just have to change this T on in terms of T minus T off, etc. And you will have to write it down. So off time is pretty easy. And for if you want, and you were talking about hysteresis current mode control. Okay, first I'll do for off time also. So we have, we erase this. Instead of this T on, I will substitute with T off, T minus T off. So it will be V in into T minus T off is equal to V output into T. So I get V in minus V output into T is equal to V input into T off. So effectively what you will get is V in minus V output upon FSW is equal to V in into T off, or FSW is equal to V in minus V output upon V in into 1 upon T off. So this is the formula for fixed off time. What is the switching frequency? Depending on your input and your output voltages. Okay. And if you want to do for hysteresis, let's assume you want to do for hysteresis. Suppose we wanted to do for hysteresis, we have one thing we have is delta IL is equal to M1 into T on. Okay. So let us consider this expression. FSW is equal to V output upon V in into 1 upon T on. And your T on is given by delta IL upon M1. So T on is equal to delta IL upon V in minus V output into L. Okay, this is M1. So in place of FSW, we replace it by this. If in place of T on, we replace it by this, then we will get the formula for switching frequency for hysteresis current control. Okay, so you will ask that from one formula, I'm getting the formula for other modulation technique and the next modulation technique. Why is this possible is because I'm just analyzing the steady state inductor current waveform and I'm deriving these conclusions. Now, if you see for constant on time, this is constant on time. So my on time is fixed. Based on that, based on using on time fixed T on, I'm getting these other variables, okay? And these things depend on your operating condition. In the next case also, for off time, fixed off time, T off is fixed. But this input and output voltages can change. And based on these changes of input and output voltages, my switching frequency will change. Now, in case of hysteresis current mode control, your delta IL is fixed. Your current ripple is fixed. Okay, because your current ripple is fixed, I will use current ripple in the formula for FSW. And I will get the formula of FSW in terms of input, output, and inductance value. Okay, so that's the way to derive the expressions for switching frequency, right? So, okay, so I'll proceed. Now we consider MATLAB information digital voltage mode control. So anyone has any doubts till now? Okay. So this is the buck converter, which has been shown a lot. There's an input voltage and here's your output voltage. And there is this Q load. So why is this Q load present? This Q load is present for creating a load transient. Okay, this is present for creating a load transient. How does it work? Is when this Q load is zero. Okay, your R load, your effective R load is equal to R. When your Q load is 1, your R load is equal to R parallel RSW. Yeah, so these are those things. 13.5 ohm, 0.33 ohm, etc. RC and RSW. Okay, so that's how we can achieve different values of load resistors. So our load can be varied in steps of 2. Okay, into two different values. And based on that, we get a load transient. The current will go from here to here, here to here, etc. And why we want these periodic things so that we can display it on the oscilloscope. Next, these are some controller gains.
Sir,
Yes, yeah.
sir,
Yes.
this RC, this RC is what? This is that R, capital R, right?
Yeah. This should be RC.
Sir, actually, sir, these sense resistors R1 and R2.
Yes,
Sir,
yeah,
what
yeah.
will be the range of these R1 and R2?
I don't remember exactly, but typically it would be like around 10K, 20K, that range. Okay.
Sir, why I'm asking is that we are saying this RSW is much lesser than RC
Yes.
to create load transient.
Yes.
Um, in that case, this R1 R2 is also parallel to this only.
No.
So,
Yes. I understand
what
your
will
question.
be the value?
R1 and R2 will be in the range of 10 kilo ohm. 10 into 10 to power 3 ohm. Okay.
Both are equal, sir?
No, I don't think they are equal because the gain KF is around 0.127 or something. So they are not equal, but they'll be in some certain range. Like,
okay,
suppose one was like 0.12, so 12.5 by 100. It could be something around like this. Maybe one resistor is of 20K and then some 140K something. I don't know the exact value. Okay. But it will be in the range of kilo ohm.
So this
R1 and R2 will be in the range of
this
kilo
R1
ohm.
R2 much greater than load
Yeah.
RC.
Yes, sir. Much greater than load RC and RSW. So if you know for resistors in parallel, when there are two resistors in parallel, let us say RA and RB, your R effective will always be less than the minimum of RA, RB. Will be less than the least of them. Always. That's a guarantee. And if one is very large, if suppose RB is very greater than RA, then you can approximate it. R effective is approximately RA, the minimum of it. Okay. That you.
So with this Q load, we are actually RSW. We are actually using to step up transient, right?
Yeah. Yes.
We can't. We are not emulating step down here.
No. See, when Q load is equal to 1, Okay. When Q load is equal to 1, your R load is equal to RC parallel RSW. Okay, that will be around in the range of 0.3. When your Q load is equal to 0, your R load is equal to RC, that is equal to 13.5 ohm. In this case, this is a step up. Okay, when Q load is 1, that is a high load condition. Because when your resistance is less, then your current drawn is more. Okay, so this is the thing to keep in mind. When your resistance is less, then your current drawn is more, and then your load is higher. When your resistance is more, your load is less, and your current drawn is low. Okay.
Okay, so since R1 and R2 is much greater than RC, it won't affect these things.
Yeah. Yeah, and we have to wantedly design and choose those R1 and R2 in such a way because it should not load your buck converter. No? Otherwise, their losses also will come. Their main goal and purpose is just for sensing. So as if R1 and R2 is made as high as possible, it is better, such that it can it will draw very negligible amount of current, and the losses in that will also be more, and it should be able to give the sensed output voltage directly proportional. Okay, and one more thing is these you must keep in mind whenever you're designing your converter, like you guys would probably after this course you would make some mod hardware prototypes. That would be something which you would be highly encouraged to do. So when you're sensing, it should be very accurate. It should be accurate. Okay. So these R1 and R2 resistors, they have tolerance of 1%. Okay, you choose them with those are like, these SMD resistors are there with tolerance of 1%. And that is the recommended for these voltage dividers, etc. To use those resistors with
SMD has
tolerance
the
of
least
1%.
tolerance, sir.
What of that?
Sir, are you saying SMD has the least tolerance?
No,
SMD resistors.
no, that depends on the resistor you buy. Like there are certain resistors which come with 5% tolerance. Suppose they come with 5%, 2%, okay, 1% tolerance, etc. If this is 10 kilo ohm and this 1% tolerance, it would range between around 10.1 kilo ohm and 9.9 kilo ohm. So between this range, okay, it is very less. But suppose there was 5% tolerance, then it would range between 10.5 kilo ohm and 9.5 kilo ohm. So as these vary, what will happen? Your gain, your step down ratio, which you have designed for, and the one which you actually practically get will change. So it is recommended to use the resistors which are very low tolerance. Yeah.
Sir, even if we are designing, we have to design for least tolerance, right? -1. Suppose we are taking -1% resistor. Actually, we
Plus or
have to
minus,
design for worst case. This
no,
-1%, right?
it's plus or minus 1%. Okay, and there's some mathematics which says when it is the worst case scenario, etc. But when you're choosing, that is when you're choosing the component, you should choose like one tolerance which is around plus or minus 1% SMD.
Choose least tolerance.
Yeah, lowest tolerance, yes. Okay, it could be SMD or through hole, that is fine, but tolerance should be low. That's better. But as the tolerance becomes low, the cost also will increase. Yeah. Then inside, these are some gains, KP, KI, KD, etc. These are gains. And ADC is 10-bit ADC, but we are discarding 1 bit, so 9-bit. DPWM resolution is 9-bit. Your clock is 100 megahertz. So this is the clock which is used to generate other clocks. It is used to generate this clock, it is used to generate this clock, etc. And this is your voltage feedback gain 0.27. So effectively your R2 divided by R1 plus R2 is approximately 0.27. Right? So that's how you must choose and design. Now, how is voltage mode control being implemented? What exactly it is? We have, we will sense sensed output voltage we will take. We will sample it using an ADC. Then that sample value will compare with the reference value. It will generate an error. That error will pass through our controller. That controller will generate a control signal VC of n. Okay, that VC of n will be something like this over here. That will be compared and that will generate my Q. Okay, this will generate my Q signal Q. And that is effectively will generate, this is fixed frequency. Yeah, this is DPWM. Yeah? So PWM. So that is why it is pulse width modulation. So frequency is fixed. Okay. So what we are changing is the on time. On time is being changed, while T is remains the same. Okay. So that's why you're using this latch, etc. And we also stuck a dead time. And after the dead time, it is goes to the main switch and to the auxiliary or complementary switch. So this is a simple buck converter with a power stage. And this is how you implement inside your FPGA. You take the sense signal from ADC, compare with reference, generate error that you pass through your PID controller. That generates a control signal which you compare with a ramp, with this sawtooth or ramp signal, and that will generate when you should reset. And your set comes from a fixed switching frequency clock. After that, you'll have a dead time module, and that will generate your high side and low side signals. And now, how do you implement it in MATLAB? In MATLAB, you just have a V reference. Okay, this is your V reference. This is your output voltage. You scale it with the feedback sensing gain. And then inside you have this digital voltage mode control module. Okay. All right. Then your V reference is compared with your V. This is your ADC. Okay. This is your ADC. This is your ADC. And this FSW1, this is your ADC clock. Okay. This is just for enabling the ADC that you can ignore. And the V reference and the V output sensed output signal that generates a V error signal, which is corresponds to this. Then how do you implement this controller? This controller is implemented over here. Okay, your digital controller, and it is triggered by this clock. Then we are adding this ramp. Okay, like the sawtooth ramp is there over here. Here we are actually just emulating a straight ramp, but because just to simplify implementation in MATLAB, and from that you generate your reset signal. Okay, this reset signal. And similarly, this SR latch over here, and we are generating the gate pulse. So, is there any doubts in this part? No doubts. Okay. So, there's a MATLAB-based implementation, and we are comparing that with the FPGA-based implementation to show how they can be synonymous. Now, we will look at certain hardware results which are there, which Sir has demonstrated. So, this is for a load step up and step down. This green one is my inductor current. This is my inductor current. This is my output voltage. My load was increased like this. This is the way my load will behave. Okay, this is the way the load current will behave. It will be the average of the inductor current. Okay. So when the load current, I output, when the load current changes from one value to the next value, how is this brought about? By switching your resistors. Okay, by changing Q load. Okay, by changing Q load, this is happening. And one more thing I'd like to mention, just to keep in mind the implementation details. this switch, okay, this switch, this will also be implemented using a MOSFET. Okay, you will implement this also using a MOSFET. And to drive this MOSFET, so this is like your MOSFET, okay, this is your MOSFET. So this is your Q load signal which comes. Okay, and here is your RSW. And this is your RC. No, this is your R. Now, to drive this MOSFET, we just require we require a gate driver. Okay, you require a gate driver. Now you could why have we placed this MOSFET below the resistor? Like we could instead have placed the MOSFET over here, right? We could have made the MOSFET over here, and over here RSW. Okay, and then we could give
Yeah,
Q
this is
load.
the ground issue.
We have made the MOSFET at the low side because we can give the gate signal with respect to the ground. Okay, this is your ground. If it was in this case, we'd have to boost it to this potential and then apply the gate signal. So to simplify, we just apply the signal with respect to the ground, and we can just use a simple low side gate driver. Okay, low side gate driver. Okay. Whereas if you recall, to implement this, here also we require a gate driver. And to implement this gate driver, we used a bootstrap arrangement with a half bridge gate driver. It was used for this. But for this we use. And now you may ask me, why are we using a MOSFET? Okay, the MOSFET we are using to turn it on and off because it is controlled by us. We can control when we want. And the rise time, like the time how much time the MOSFET takes to turn on. Like if MOSFET will turn on very fast, okay, turn on very fast. This time will be in the range of nanoseconds. If this is very small in the range of nanoseconds, then it approximately looks like a step. Okay, it will approximately look like a step. So that's why we are using these MOSFETs to do that. Otherwise, you could also, like, if you use this rheostats, etc. Suppose you have a rheostat and you try to vary it. What will happen is it will change. No doubt your resistance will change, but it will change it will take like a time. While you're changing it, when you're moving it, it will take around 1 second, 2 seconds, something. Okay. Suppose even if it was very smooth and by chance you also do quite fast, it may be in the range of milliseconds. But that milliseconds is still quite, so if it was milliseconds, what will happen is it will be changing like this. It will be changing like this. There will be some time. Okay, this is known as your slew up time. Okay, that is in the range of milliseconds. But in the case of MOSFET, it is in the range of nanoseconds. Okay, so that's why we use this sort of arrangement to bring about what is known as a load transient. Load transient. Okay. So what actually is a load transient? It is like a sort of disturbance we are giving. And when the disturbance occurs, we want to make sure that this output voltage remains the same because this converter is basically a voltage regulator. It is supplying power, and that power which is supplying, it should be at a certain voltage. The voltage from the output should be fixed. It should be regulated. That is why whenever certain disturbances occur, it should be able to reject those disturbances. That is load transient. So let us consider this. This is my load transient thing here. Okay. So my load has increased. Okay. My MOSFET has been turned on. You will see your output voltage starts falling down. It starts falling. After some time, it starts rising. So why is this happening? So when you have your capacitors over here, okay, you have your inductor over here, capacitor. This is your load. Okay. This is your IL. This is your I output. This is your IC. what happens is suddenly your IO output becomes 2 times IO output. Okay, if this and your IC, suppose IC1 is equal to IL minus I output. Then suddenly IC2 becomes equal to IL minus 2 times I output. What will happen is your capacitor current will reduce, and because your capacitor current will reduce, the output voltage will start dipping. It will start dipping. Then as your inductor current is increasing, your inductor current has increased. Then
Sir, if
slowly,
there is,
yes.
sir, if there is no resistor also,
Huh?
DCR also, then also there will be a drop in the voltage.
DCR of which DCR is for your inductance, and that is not considered here.
Oh, okay, ESR for capacitor.
Okay. ESR of capacitor also is there. Yes. Yeah.
If there is no ESR of the capacitor, will there be drop in the output voltage?
Yeah, it will be there. No, there's there. It is there. Okay. It will be there because see your capacitor. This is your capacitor. It is maintaining some voltage VC. This will the average value of VC will remain the same. Will remain the same if the amount of charge Q charge and Q discharge are the same in one cycle. So, like it would be like this. The charge would come something like this. Okay, this is your I capacitor current, capacitor current. It will be like this. This will be your Q1, Q2, and Q3. Okay, because charge is a product of current into
Sir,
time. Yes.
sir, but in the with the ESR case,
Mhm.
the dip will be much more deeper, right?
Yeah,
Compared to without.
in the when there's a ESR case, there will be a discontinuous jump. It will be a jump like okay. First, let me just show this. Okay, first let me just show this. So your voltage was assumed over here. Your voltage will here. This your voltage is reducing till here. Okay, sorry, this curve is not correct. Your voltage is reducing, and as long as your capacitor current is negative, your voltage will reduce. Then when it becomes positive, your voltage will start rising. Okay, it will start rising. Then again, when it becomes negative, it will start falling. It will start falling. Okay, so your average value of your voltage is fixed. Okay, your average value of the voltage is fixed, and at the start to the final time, these values must be the same. Then we say that it is operating in steady state. Okay, it has reached nominal condition, steady state operating condition. Okay, and now you're talking, this is for a steady state case, your capacitor current. Now what happens when your load increases from I output to 2 I output? What happens? Your capacitor current becomes further negative. Okay, it becomes further negative. So your output voltage will dip more. And then it will be like this, it will increase like this. And as it is increasing like that, your output voltage also will start increasing. It would be something like this. Okay.
Sir, like instantaneously the voltage across the capacitor can't be changed, right?
Yeah, it is not instantaneously changing. Over here also, if you see, it is not instantaneously changing. It is reducing. It is reducing. Okay, it's not like this is the output voltage. This is your V output. It is reducing. When your inductor current is not instantaneously changing, it is increasing. It is gradually increasing till it finally reaches the next steady state condition. Okay. Or any doubts?
Sir, this load,
Hmm. Yes,
Sir,
yes,
here
tell.
we are saying about this step up branch. This is the average current, right?
Yeah, average current, yes. See, for your
Sir, that
tell.
okay. For sir, that but the average current also will not be having a step as we draw now, sir. It will be gradually increasing only.
Mm, This just see this inductor one. This is your inductor.
So
You're
in this
able to,
waveform we have drawn.
yeah, this one, right? This one, right? This step, right? You're talking about the
Yes,
Z
sir.
curve. This is your output load current. Output
This
load current. Your
yeah.
output load current, why is it changing in a stepwise manner? Because you're turning on and off the MOSFET. Okay, remember, you're turning on and off that MOSFET. And that resistor is getting connected and disconnected.
Yeah, but
Mm-hmm.
yes, sir. That average of inductor current is the output. So output current won't be having this step. It will be
No.
increasing along this inductor.
Your capacitor current is IL minus I output. And in steady state, your average capacitor current is 0. So your average inductor current is equal to your average output current. But during transient, this is not valid. During transient, these are not valid. Okay, the average values are not 0. This is not 0. This equation is
Yeah, sir.
always
Just now
valid.
you explained. Now I understood.
Yes, this is valid.
Yeah, this one is IC1 equal to IL minus I naught. Through this
Yes.
you explained.
Yes.
Okay. Okay.
Okay. So meeting will end now. I'll again start it. Okay. So similarly, this is the simulation result of how the inductor current waveform is happening during the step up. Okay, when the current is stepping up from a low load to a high load condition. Correct, and then similarly, this is the simulation result for the wave voltage. Okay, you see the voltage is dipping. It is reducing as your current is increased, and then it is slowly recovering and coming back. It is slowly recovering and coming back. And this is, your how much it is you undershoot in your output voltage. So this is the hardware result and this is the MATLAB simulation and they closely match. Okay, so your load current is changing from 70 milliampere to 3.07 ampere at 3.3 volt input. Okay, so how did we come with these magical numbers? Why are these magical numbers there? Because in one case your R load was 13.5 ohm. Can anyone do 1 upon 13.5? 1 upon 13.5.
0.074.
0.074. It is 0.074.
Sorry. Yeah,
So 0.074. So that approximately corresponds to 70 milliampere. Okay, when your R load is approximately 0.3 ohm, then this corresponds to approximately 1 by 1 upon 0.3. So that corresponds approximately 3 amperes. Okay, 3 amperes around that. Okay, so it depends. Here we have just taken an approximation. So if you have just if we did 13.5 parallel to what is this value actually? Is 0.33. Okay. Then probably we would have got more accurate value. Okay, 13.5 parallel to 0.33. This is the hardware related MATLAB implementation. So are there any queries in this? Okay, no query, we proceed. This is for the load step down transient. Okay, this is a step down part, and this is how the step down waveform also is being shown. No, sorry, this is not the step down. This is the step down. This is where the load has stepped down. The load was over here. It is Okay, from here, it steps down like this and continues like this. Okay, this is your load current. So when this is stepped down, what happens? The capacitor has excess charge, and so the voltage increases. And then the inductor current slowly finally settles to its new operating point, and the capacitor also finally gets regulated to the 1 volt. And why is it being regulated back again at 1 volt? Because of the closed loop. Okay, because of the closed loop. This is okay. Okay, so this is the MATLAB simulation result of the step down of the inductor current is shown over here. And this is for the output voltage, how there's an overshoot. Okay, there's an overshoot. Because your load current has reduced. Your load current has reduced, but your inductor current does not instantaneously reduce. And because of that, there is this rise in your output voltage and finally it gets regulated back. Alright. So any queries in this about the load transient? Okay, so I'll proceed. Now we'll do a reference transient. So what is a reference transient? You know you have the Vref plus minus V output that generates your V error and that goes to your PID controller or your whatever controller you're using. Suppose initially my Vref was 1 volt. Then I take it from 1 volt, I take it to 1.1 volt, and then I bring it back to 1 volt, etc. In this case, I'm giving a reference step up transient, and in this case, I'm giving a reference step down transient. So the output voltage, which was at 1 volt, finally reaches 1.1 volt, then again goes back to 1 volt. Okay, so this is your reference transient is shown over here. So when this is a reference transient, what happens? Your inductor current, but your load remains the same. Your I output remains the same. If your I output, average value of your I output remains same, then your average value of inductor current also should remain same in the steady state. In your steadies. No, there's one minute. This is your Vref corresponds to your output voltage. So initially output voltage was 1 volt, then it becomes 1.1 volt. Okay. Suppose your load is still 13.5 ohm. So in this case, your load current is approximately 70 milliampere. While in this case, your load current will be approximately 77 milliampere. Is this clear? Or are there any queries in this? Okay. So there will be a slight increase in your load current also will slightly increase. Because why is that happening? It's because your output voltage is increasing. Your output voltage is increasing from 1 volt to 1.1 volt. And this is how the output voltage is increasing from 1 volt to 1.1 volt. And this is for step down. Because at some value it steps down like this. Your load current will finally go down to a little lower value. And this is for your output voltage. Now it changes from 1.1 to 1 volt. It is slowly coming back. Okay. Now this is the waveform from the oscilloscope. Okay, this is your oscilloscope waveform. Now this is a side by side. Okay, we are not able to perfectly compare how much is the deviation. Where are we? What parameter have we? Is there's a mismatch or what is the reason? We can get some brief or some sort of a value or some sort of deviation we can see, but it would be good if we can plot them both simultaneously. So for that, what we have to do is this oscilloscope. This is the data in the oscilloscope. We have to take it in our pen drive, and then we have to plot it in MATLAB. Okay, this is what is done. So that will be shown in the next part. So this is my oscilloscope data. So this is the Tektronix oscilloscope. This is my output voltage. This is my inductor current. All right. So there are these USB ports in which we have inserted a pen drive. A pen drive has been inserted, and this is your whole test setup. This is your power supply. This is your current probe. Okay, this is your current probe. And this is your voltage probe. Okay, so this is how your current probe is like a clamp around this sort of wire, so that it can show your inductor current. Okay, this is not your sensed inductor current. This is your displayed inductor current. It is displayed via this current probe. Okay, and this is your output voltage, which is displayed by this voltage probe. All right. Any queries?
Sir,
Yeah.
is this current probe is also called as a differential probe?
No, this
Is
is not
that
a
the
differential probe. A differential probe is like that isolated probe. Okay, so whenever you're doing your one thing practically, see there are these channels: one channel, second channel, third channel, fourth channel. Okay, the current probe is independent. Let us leave that. These three channels, or all the channels of the oscilloscope, they will have a same ground. Okay, they will have a same ground. Okay, and because they have the same ground, you must be very careful that see, this is your pin. Okay, this is your, if you see your voltage probe, this is your voltage probe, and this is your ground part. Okay, this is your ground, and this is your signal. So your voltage probe has two parts. One is the signal part, and one is the ground part. Now the ground of probe 1 will be same as the ground of, should be same as the ground of probe 2 and same as the ground of probe 3. If not, you will be shorting those two terminals. Okay, let me just show you a connector.
okay. So if there are two different grounds in a circuit, then we should not be using same probe from these adjacent to measure the voltage, right, sir?
No.
If suppose
Okay, let me understand.
if suppose in the circuit
Mhm.
there are two different grounds, suppose in some isolated converter,
No, yes.
there are two different grounds.
Okay.
Sir, at that time, suppose at the first probe I am measuring voltage with respect to one ground.
Understood. Okay.
Then second probe, I should not connect to the, what do you say? I should not connect to the second ground, right, sir?
Yes.
Which
yes,
means
yes.
I'm shorting both the grounds.
Yeah. Yeah. So in that case, you need a differential probe. In that case, you need a differential probe. And differential probes are very costly.
Can you please explain this concept?
Sorry.
Could you please explain this concept?
Okay. 1 minute. Okay. So suppose there's a transformer. Okay. This is ground 1. This is ground 2. They are electrically isolated. So suppose I connect a probe over here. This is a ground of probe 1. And this is ground of probe 2. Okay. This probe 1, probe 2. What will happen if I connect both these probes to my oscilloscope? Then what will happen? Ground 1 is connected to your ground 2. And that is not desirable. That could result in a malfunction of your circuit, etc. So
That is the concept of floating voltage, sir.
floating voltage is not, this is not related to floating voltage currently actually. Floating voltage is like at a point the voltage at that point is not exactly defined. It's not exactly defined. Could change.
Okay.
And we
Actually,
don't
the point here is
tell.
while I'm searching for the benefits of isolated and non-isolated differences, then I found somewhere like floating voltage, but I didn't get the concept which was there. That's the thing I'm asking you.
Sure.
Okay, sir. I'll share you the link.
Okay. Yes, send it to me later. Okay.
Okay, sir. Thank you.
We don't. So whenever you're testing, right, it is advisable that if you have these differential probes or isolated probes, then it is fine. Okay. What those differential probes will do? They will tap your signal. Suppose they will tap your signal from here and here, and then they will have internally some isolation, and then it will get converted to the ground. Okay, then it will get connected to the ground. So that is fine. But in case these are non-isolated, then it is not correct that this ground should get connected to this ground. That is not acceptable. Okay.
Sir?
Yeah. Yes,
Sir, suppose we are using in the circuit that you have drawn in transformers.
Yes.
Suppose if in this case, in the primary and secondary, if I want to measure the voltage, then I need to use two different DSOs.
Yeah, you could do that. Or you could use differential probes. Isolated differential probes.
Okay. Sir, how can I know that these probes, these slots, this PNC connector, some name is there?
This, okay, I don't know. This is
This,
connectors.
yes, sir, that one. Yeah.
Yes.
How can I know those are isolated or non-isolated, sir?
Mostly it will be
Inside.
Internally they are all connected. Okay, because most normal oscilloscopes. Okay, these are non-isolated oscilloscopes, and these itself are very expensive. Isolated oscilloscopes will be very expensive. Okay. So the normal lab, general purpose lab oscilloscopes, they all are non-isolated. They're all the grounds, where the ground of this and the ground of this and the ground of this all are internally connected.
Sir, is that can we in our multimeter we'll have one terminal to connect to test the short. Using that, if I touch both the
See,
can I say whether it is internally connected or?
See, if you connect, okay, to check whether those two are internally connected.
Yes.
You could do. I don't know. Like, see, this is a entire probe. Okay, the probe, it has certain connections so that one goes to your internal and one goes to your ground. I think the outside is the ground or something will be there. So you should know which is the ground part and connect it there accordingly.
Okay.
Yeah, so you can check that on the multimeter. The advantage, like one of the ways is if you connect a probe, if you just connect one ground, then the next other probes you don't need to connect the grounds because they all are referred to this ground. Okay, that is one advantage is there.
Yeah, that is if all the grounds are same. If it is
Yes.
different, then we have to go for differential.
Differential, yeah. So that's how we insert a USB over here. And then there's, see over here, there'll be something save button. Something. So that save button will be pressed. No, menu. And then we can, save the waveform, save the image, etc. So you have to, these options are there. Okay. And then either you can save it as an image. Okay, if you save it as image, it'll come in .bmp format. You could also convert into other formats also based on the settings of the oscilloscope. And then you can save image. Okay, you save them. You can save the screen image. If you say that you want to save the waveform, then it will be a .csv file. So .csv file is your Excel file. Okay, this is your Excel file will come. Okay, and how that, okay, and then it will be saving. Okay, it will take some time to save. It will not happen instantaneously, and that will be seen over here like this. Okay. And okay, this is done. Yeah, so this is how your CSV file will look like. Okay, it'll tell which oscilloscope, what is the version of firmware, what was the sampling period, what were the offsets, etc., the time, channel 2, channel 4, etc. All the data will be saved over here. Now,
Channel 4 is current version.
we will see now. Channel 4 is current, yes. Channel 4 is current, channel 2 is voltage. So your voltage is approximately 1.05, 1.076, 1.06. This is your output voltage. So you can use this sort of MATLAB code to, what you say? Okay. So this data file, Excel file, you can read it into MATLAB. Okay, it will come in from data. Then in the first column, third column, second column, third column, which all data is there, you can take it. And then you can plot the data. Okay, you can plot the data. So this is your voltage plot. Okay, but there'll be a time offset. Why the time offset is there? Because if you see the CSV file, time is starting from minus 2.11. It is not starting from 0. The certain time offset is there. Similarly, for your inductor current also, this is the time offset will be there. So what you have to do is, you must instead add to the 0, the plus 0.25 you must add. If you add everything 0.25, this will be 0, this will be your 0.05, this will be your 0.1, etc. Okay, that's why you must add to the first column. First column, which is your time vector, you must add this offset. Okay, around like plus 0.25 you must add. So that will start from 0, 0.001, 0.002, etc. It will proceed. Initially, it was what it was. It was minus 0.25, minus 0.249, minus 0.248. Then when you add plus 0.25 to all these elements, then it will start from 0, 0.001, 0.002, etc. Okay. So that's why we will take the oscilloscope waveform data. Okay. Yeah. How we must take the offset, etc. Exactly. Similarly, this is your hardware result is the green one, and the red one is the simulation result. So we plot them side by side. Okay, we adjust the offsets accordingly. So that they can be plotted side by side. So now we can visualize and see how much is the difference between each of these curves, etc. How accurate is our simulation result? Probably what is the reason or cause for the deviation also we can check. Okay. Similarly, this is your output voltage waveform is shown over here. This step down transient, and this is the voltage waveform. So now we will start with. So are there any queries till this part?
Sir,
Yes.
No,
that here we'll be having, in that DSO, we'll be having 3 probes and then 1 current probe.
This one. You're talking about?
Yes, sir.
Yeah.
So we have a 3 voltage probe and 1 current. Sir, what is the last one? There is 1 probe, is there something connected?
I also don't know that. I have not used it actually. I have not used it. Probably it is for certain triggering of the oscilloscope or some advanced feature, which might not be needed for it. I haven't used it. Yeah. Yeah. No, you see, and one more thing, it's not necessary that you will have 3 voltage probes and 1 current probe. You can have 2 current probes and 2 voltage probes, etc. Okay, that is not fixed.
Sir, I'm having a sir.
Okay.
This voltage waveform, this inductor current waveform we are taking from the DSO. And because since it is not starting from 0, we are offsetting it and comparing with the MATLAB.
Yes.
Comparing with the simulated waveform.
Oh.
Sir, here, sir, how? So all the lowest point of the inductor current at all instances are in our simulation and DSO they are matching.
They are approximately matching, yes.
Well,
you're talking about this one.
Yes, sir. Yeah, this one. The IL min is matching. The instant at which IL min happens in both the waveforms is matching.
Yeah. Instant at which it
at
is
all
happening
values
will be same because it is fixed frequency, man. No? It's fixed frequency, no? So when it is set in, it is fixed frequency, right? Fixed frequency operation. This time duration is fixed, no?
Okay.
So when it will turn on, it can be synchronized. Okay. Then matching.
Sir, what I'm having doubt, sir.
Yeah. Tell.
Okay. Sir, actually, if the sampling frequency of DSO for our for constructing our CSV file.
Yes.
If the sampling frequency of DSO is suppose it is not capturing this Imax.
Okay. Yes.
Is there a possibility, sir?
That usually.
Then how can we say that it is matching?
No. That could happen in case you're going for very high frequency. That depends on your oscilloscope. Okay. So, like if it is, let's say, I'm actually seeing a 200 megahertz oscilloscope. 200 megahertz oscilloscope. Okay. So the sampling rate can be approximately 5 nanoseconds. 5 nanoseconds. Okay. So this is quite a small enough time. It can take quite accurate values, accurate range of values. The resolution is so small, 5 nanoseconds, but can be quite accurate. It depends on your oscilloscope, actually, on your capability of your oscilloscope. And one more thing I'd like to tell, see, when you're doing these hardware things, there's something, these probes are here, right? These probes are there. You can test the probe. Let me just check whether any this. Okay, you see over here, this is the ground and this pin is there. So you can connect the probe and over here, and it should show a square wave. So it should show a square. Hook-like thing will be there. So show 2.5 volt amplitude and some particular frequency, say 2 kilohertz, etc. So that should be seen. Then you can know that your probe is working. Okay, that is to test the probe. Okay. Sometimes the probe, will have some multiplication factor. Okay, so to check that whether that is working, what is the scaling factor currently, all that you can use these things. So this is also provided. Similarly, you can measure feature is also provided. This is used for changing the vertical zoom. This is used for changing the vertical position. Bring this up or down. Correct? This is now suppose 2 volt per division. If you change this, you can make it 4 volt per division. All these are there in the oscilloscope. So now we will go for loop shaping design. for digital voltage control. So this is your block diagram, okay, for FPGA implementation is shown over here. Your feedback gain is 0.27 and this ramp voltage maximum value is 2 volt. So this is how the controller is shown. This is the loop diagram. This is your controller GC. This is your sensing gain KF. This is your delay. Time delay is there. This is your modulating gain, which is 1 upon Vm. This is your GVD. That is your duty ratio to output voltage perturbation. Output voltage. Then your output voltage perturbation is the sum of this duty ratio input plus this disturbances, changes in your input voltage and changes in your output current, load current. All these will affect how much your output voltage will change, and that is again being fed back by the loop. And so this is your closed loop. Okay, this is your closed loop. Okay, and this is your loop gain. Your loop gain is the product of all these transfer functions which are there in the loop. Okay, this is your loop gain. So your K loop dash is equal to GC into e raised to minus tau d into FM into GVD. This KF and KF cancel out. Okay. So any queries in this? And then we can even take the feedback gain over here. So sorry, someone was yes, Sir,
I have a doubt in GVD.
Yeah, GVD, okay. What about it?
Sir, I want to know the quality factor in that case, like Q0. How we are getting Q0? Like intuitively, can we say the quality factor from the circuit diagram?
No, see, for a second order system, this is like something will be here, this is your denominator, okay? So your 2 zeta is equal to 1 upon Q. 1 upon Q. So quality factor is 1 upon 2 zeta. So based on the transfer function, you can get what is your quality factor. Basically, what your quality factor determines is in your Bode plot. This is your Bode plot. This extra peak is because of the quality factor. If the quality factor is high, then this peak will further increase. It will be more and more. If the quality factor is not that high, it will go like this, will go like this, etc. This is just basically the quality factor. Gains.
Like, can we say, like, from the circuit diagram, we have there an L inductor with series resistance, a capacitor with series resistance, and a resistor R is there, load resistance.
Okay.
From that, can we intuitively say the quality factor? Can we write? If yes, how we can do so?
Yeah, for that you'll have to write the expressions and like you'll have to derive the transfer function and then you can write the quality factor expression. But in a normal case, we ignore those resistances, etc., because they are quite negligible. And unless you want a really accurate one, you can ignore them.
For series RLC, it is 1 by R into root L by C.
Yes, okay.
Sorry. 1 by R into root C by L. The
Okay.
quality factor for series RLC.
Yes.
For this kind of combination, how we can calculate that? I want to know.
No, no, no. Your GVD of S, assume it is 1 upon S square plus 8S plus 9. Okay? This is your transfer function you get for GVD of S. Then what you do, you compare it with omega n square 9. So you will get omega n is equal to 3. And 2 zeta omega n is over here. You get 2 zeta omega n is 8. So 2 zeta into 3 is 8. So 1 upon q is 8 upon 3. So quality factor is 3 upon 8. So that's how you get a quality factor, right?
Yes, okay. This is clear, but I want to write the intuitively for a given circuit which we have the small signal model.
Hmm. So you just have to use whatever. This will be in terms of R, L, etc. This will be in terms of L and C, something like that. So
Yes,
that
sir. Yes, sir.
expression you have to do it, and you have to use it.
Okay, sir. Okay.
Yeah. Oh, so this is the loop. Okay, this is your Q, your quality factor, Q, omega naught, etc. Now, yes, this is the expression of the quality factor in terms of R, C, RE, characteristic impedance, ZC upon R, etc. This is your characteristics
Sir,
ZCs. Yes, yes, yes.
sir, actually in our basic circuit, if you take RL, if there the physical significance is if a Q factor is high, then the inductor is closer to the pure inductance.
That is for inductor. Yes, yes, that's for inductor.
Yeah. So similarly, what is the significance of this Q?
See, that is a first order system. That is a first order system because it has me RL.
Yeah.
And that quality factor is just
Okay.
basically how accurate how low the resistance of the inductor is. That is how well designed the inductor is. But in this case, the quality factor, it is a second order system. So when you analyze the second
Yeah,
order,
you said it is 1/2 zeta.
yes, 1/2 zeta. So if the damping is less in the circuit, then your quality factor is more. See, just assume there's a R, L, C, etc. Okay. So if your R, if you see, if your R is small, if your R is tends to 0, if your R tends to 0, then what will happen? It will be very oscillatory. But as your R increases, these oscillations will die down. Okay, it becomes damped, becomes more damped.
Okay.
So as you increase R, your quality factor will reduce and it gives a damped response. Now, why this is important in our case? Considering for our case, we give a step input, step output. Okay, if the quality factor was very high, the output will oscillate like this. Okay, if it is quality factor is quite low, it would go like this something. Okay, now these oscillations might not be permissible because it was supposed to be regulated at 1 volt, but now it is reaching around 1.3 volt, etc. Such high overshoots and all may not be permissible. Okay, so that's why we have to select a suitable Q quality factor. Now the quality factor cannot be too low that it will take like so much of time to reach. That is also not desired. We want it to be quite fast enough to reach in quite minimum amount of time, as well as to have less overshoot and undershoot. So in
This is for all. Okay.
In this context, we use quality factor to do that, and also that is why we use phase margin, the concept of phase margin. So your quality factor or your damping are closely related to your phase margin, and based on for a second order system, we have what we say a relation between phase margin and Q and zeta, but it is observed practically that as your phase margin is increased, your zeta increases, and your system gives a more better damped response. Okay.
This is for some higher order.
This for the second order system, you have an exact formula which you can use, but for higher order systems, you just intuitively it is observed that as you increase phase margin, it is more damped. But you'll have to see and try to understand. This you can actually refer to this Maximovich book, Fundamentals of Power Electronics. So this is a very useful book. in which he
Okay.
has yes, tell.
Name.
Hmm?
Name, please. Name of the book or something else.
This fundamentals of power electronics.
By
Maximovich. You can just check fundamentals of power electronics, you will get it. It is a very standard book. Let me just put Dragan Maximovich. Fundamentals of power electronics. So I think it's in chapter 9, I think these concepts are there. So this is the book. Fundamentals of power electronics. Okay, is it visible for everyone? This is Robert Erickson and Dragan Maximovich. They also have a course on Coursera where they are explaining all these things, where they've explained many important things, which is very useful. As well as so referring to this chapter. Yeah, over here, they've discussed about phase margin, etc. Phase margin, damping factor, transient response, damping factor. All these things are explained in chapter 9. Okay. Controller design. Chapter 9, controller design, phase margin, damping factor, all that they have discussed. So you can refer to this one. Okay. So we are using a PID controller. Okay? We are using a PID controller, and this is a transfer function for the PID controller. And then we write it in this form. We rationalize them. K1, what is K1, K2, etc. We have. Tau also is RCMC. Then you will do pole zero cancellation. That is, these second order transfer function will be cancelled by this. They will cancel out. Okay. And your this will cancel out with this. Okay. So in that you will get a unity, you will get a loop gain which just has 1 by s in the denominator. So just explain better. Okay, this is your K loop. Okay, is your K loop Fn into Vn upon alpha into 1 plus s upon omega ESR 1 plus s upon q omega naught plus s square upon omega naught square into your GC. What is your GC? This is your GC, okay? This is your GC. Into Ki into 1 plus K1s plus K2s upon s into tau d of s plus 1 into Kf. So what happens is, so cancel out this and this. We cancel out this and this. And when you do that, you will find the effective K loop of S is Fm into V upon alpha into Ki upon S into Kf. So this is your loop gain. Okay, gain loop of S. So based on this, you will have to set your crossover frequency. Thanks. So there's one more thing I forgot to add. You have a delay. E raised to minus s tau d also will be there. This is the delay which will be there. Okay. First, is there any questions in this part? In this part, is there any question? Hello.
Sir,
Yeah.
sir, this tau. Sir, how can we make this tau d equal to omega E, sir?
Okay.
1 by omega E, sir.
This is just
practically.
Practically you cannot do. Practically you cannot do it. This is just a theoretical way. So what this entire procedure, it is just a way to get the initial set of gains. You get an initial set of Kp, Ki, and Kd. You get it. Okay. Then what you do, you run your system with these gains. Then you will feel that probably you have to increase something or change something or vary something. Then you can vary them around these values which you got, and you can check the performance of the system. Okay, because there are many things which you haven't modeled also. There are many things which you have not considered, and those might be affecting it. Those might be making the performance poor. Those might be making it a bit more oscillatory, a bit unstable. So then once you get these gains, these are the initial set of gains. Then you can play around these gains to get a better performance in your actual hardware. Right? It is not possible to exactly cancel out. It is not possible to exactly cancel out. But if you see, root locus, control systems, etc., when the zero and the pole are very close to each other, their effect on the overall response of your system is negated because they are very close to each other. Something similar can be done, right?
Okay.
So in this way, your K loop of S is some Fm, Vn, alpha, Ki upon S into Kf. If you draw the Bode plot of it, it would be something like this. It is just a reducing thing. Because it is just some gain K upon S. Okay, it will be reducing at a slope of minus 20 dB per decade. So at low frequency, your loop gain is very high. The loop gain at low frequency is very high. Okay, and at high frequency, it is reducing. And if time at which it crosses the 0 dB, that is your crossover frequency. And based on your crossover frequency, you get a certain phase margin, depending on how much phase was present. Okay. So this is the phase margin test, and that you can also refer to that maximum book which I showed to you.
Sir, how can I consider omega C, sir? Like, how can I select?
How do you select omega C, right? How do you select omega C?
Yes, sir.
So at omega equal to omega C, your magnitude of K loop is 1. Okay, magnitude K loop is 1. How can I do that? You see K loop of S, let me just go to this here expression of K loop of S. Okay, let me go here. K loop of J omega. What is K loop of J omega? It is some constant K divided by J omega. Okay, so your K loop of J omega, the magnitude of that is K upon omega. Okay, it is just K upon omega. If I set the value of K, now I set K to be equal to omega C. Then my K loop of J omega, when my omega is omega C, will be equal to K upon omega C. And since my K is equal to omega C, this magnitude will be 1. Okay. Let me repeat, my K loop of J omega comes in terms of K upon J omega. Alright, for the magnitude, I take the mod. This J in magnitude term, it has a value of 1. It doesn't come into the picture. So it is just K upon omega. Now I have to set K to be equal to omega C so that when my frequency is omega C, it will be k upon omega c, it will be equal to 1. So my magnitude of k loop will be equal to 1 at the frequency omega c. Okay. And to do that, I have to select this ki accordingly. Select this ki accordingly such that it comes in terms of some omega c and certain constants.
Sir, if that
Yes,
is the case,
that is the. Sorry.
actually here some sound is there. I'll talk.
Okay. Okay.
Sir,
And
like omega c, you are sir, it is clear
yes,
now.
yes,
Like
yes.
omega, you are saying k loop of j omega is k by j omega.
Mm-hmm.
Sir, I'm not getting. Sir, could you please repeat it?
No, wait. This is my k loop of s. Yeah? K loop of s. This is my k loop of s. Huh? This fm, v, and alpha, ki, and kf, they are just some constant values. Right? So I replace it by k upon s, right? This is fine. Fm, v, and alpha, ki, kf, they are just some constant. So I replace it by one effective new constant, capital K.
Okay.
And then my k, instead of s, I put j omega because frequency response. So be k upon j omega. J has a magnitude of 1. This k upon omega. And that's how I set k to be equal to omega c. Okay.
Okay.
Okay. And similarly, we can, the phase also at that particular frequency will be minus 90. This introduces minus 90 and it is minus e raised to j omega tau d. And this magnitude also is equal to 1. Okay. So the phase contribution is minus 90 because of this and minus omega td because of this. And then you can select a particular phase
Sir,
margin.
omega
Yes.
TD, sir, omega TD is in radians, right?
Yeah, correct. So that you'll have to,
Okay.
in your code, you'll have to accordingly make it into degree. Okay. In your code or your calculations.
Okay.
Yeah.
Sir,
Yeah.
sir,
Yes.
without suppose if you are taking a differentiator KD,
Okay.
differential gain,
Uh,
sir, if we take the ideal differential
okay.
differential gain,
Yes.
only KD without tau d,
Mhm.
sir, please can you compare those two things? Sir? If with tau d, what happens? Without tau d, what will happen?
Okay.
When
Okay. In that case, this 0 will not get cancelled. In that case, this 0 cannot be cancelled. If the 0 cannot get cancelled because that
yeah,
tau is
sir, that's okay, sir.
okay. Yes.
Sir, I'm not asking with this K loop. Generally, that
The physical
tau d,
significance. Okay.
yeah.
Okay, let us see that where's the GC. This is the tau d. So it is like a filter. It's like a low pass filter. This tau d s plus 1 acts as like a low pass filter. Okay, and this also will be present in your op-amp. In your op-amp, it will have a limit. It will have a limit. It cannot be cannot accept frequencies of very high range. There will be certain frequency from which it starts attenuating the output. So that is effectively modeled as tau ds plus 1.
Sir, when this tau d is not there, it is simply only KDS.
Yeah, but that is physically not
For
possible.
ideal.
That is for ideal
Sir,
case.
but what will happen? What will happen then? The attenuation won't happen at all. It will be sorry,
Yes,
amplifying. If only KDS is there.
If KD of S is there, see, at high frequencies, I'm talking about high frequencies. Okay, at high frequency, what happens? Then high frequency is basically noise. And in a differentiator, if it just directly responds entirely to the noise, it will result in improper operation. It will, erroneous results will happen because noise is something random, right? It's not desired. So to attenuate that noise, we have this low pass filters added. And that low pass filter is physically realizable using either we connect some RC network across the op-amp, or inside the op-amp itself, at after a certain bandwidth of the op-amp, it starts attenuating those frequencies, and so that it effectively brings about this tau ds plus 1. Okay. So I'll proceed. So this is a simple pole geo cancellation and how we get this K1, K2 cavity. Alright, and how do we convert it to digital domain? We convert it into digital domain. Then similarly, the output impedance is the output impedance. If we derive, it comes in this format. And because of the closed loop, the effective output impedance comes in this format. Okay, and so this will sort of improve the disturbance rejection. The disturbance rejection is improved because of the closed loop. And that also is given in that maximum loop. Then another method of tuning is there, which is known as the alternative approach, which also Sir has taught. Now we will consider the load step transient results. Right? Sir has used these gains, and this is how the transient response is behaving. So there's a step up, and the output voltage is reducing. There's a step down, and then the output voltage increases, finally it cuts back to regulator. Okay, that is given alternatively. That is for load step up and step down, and this for reference step. Reference is increased, reference is reduced. So this is the behavior of the system. Any queries in this?
The alternative approach has a better results, right?
Yeah. Hello.
Hello. Yes, sir.
Yeah,
Like,
yeah,
which is the better thing? Alternative approach is the better thing, right?
yeah. Alternative approach is the better one. So these are just the results are there. Now I'll consider load current feed forward. Okay. Now let us consider current mode control. This is current mode control block diagram. There is a reference output, and then the output is compared, generates the error, passes through your controller, generates a control signal, that generates a reference value. Okay. In the normal case, this I output would not be there. In the normal peak current control. Normal peak current mode control. But now we are adding this I output externally. So why are we adding the output current directly over here? What do we gain? So what happens is whenever there's a change in the output current, whenever the output current changes, instantaneously its effect can be seen in your controller instantaneously. Direct. That is why it is known as feed forward. We're directly feeding the changes in your output current. If this was not there, what happens is when your output current increases, your output voltage starts reducing. As it reduces, this reduces. Then as it reduces, your error increases. So your error increases, then your NCON will increase. So this will increase, then your NP will increase, and effectively your duty ratio increases. So this is how closed loop control works. This is the concept of closed loop control. What happens? Your output current increases when there's a change, sudden increase in output current. Your output voltage will start falling. The error will increase, and that error will the controller will increase the control signal. That control signal will increase the reference current, and that will effectively increase your duty ratio. This is the concept of closed loop control. Now we are doing this closed loop thing, but the problem is this output voltage will reduce slowly. Okay, for it to reflect the change in the output current, it takes some time. Okay, and that is a slow process. Instead, if you can just directly feed that information that, oh yes, there's been a change in the output current, and so accordingly you have to change your duty ratio. Okay, in a sort of directly we are giving that information, then it would improve the performance. And so that is the concept of load current feed forward. Okay. Is there any doubts in this? Hello.
Sir, you have explained this concept like closer loop IOT increases. Is that without feed forward or with feed forward,
It is
sir?
without feed forward. That is the concept of closed loop. That happens whether feed forward is there or not there. Okay.
But if there is feed forward, it tracks a very short within short time, right? How
Yeah.
can we explain that, sir?
See, when this feed forward, what happens? The NP is changed in effective NP. This is your effective NP effective. Okay. NP effective is changed almost instantaneously. Just changed almost instantaneously. And so it will improve the performance. In case NP effect, in case this was not there, your NP to change, it will take some time. It will go through the entire process to go through. Okay. And because of that, it will slow down. But if you can directly give the information and directly change your NP effective, then it will improve your performance. Okay. So I'll proceed. So this is how it is implemented in the FPGA. Like we know what is the step change. We know what is the step change we are giving. So we are directly giving those values. Okay. So when there is these load step transient occurs, you will observe that the dip is okay. This is without feed forward. This is without feed forward. So there's a dip and there's a rise. The load has stepped up, load has stepped down. This is for without feed forward. But with feed forward, you will see this has been reduced. Okay, over here it is virtually not there. And here it is reduced. Okay. Any queries? And the next case, case 2, where we are just using 90% of the load current, then also it is giving quite a good performance. Hmm? Yes, yes. Mhm. You
Sir,
repeat?
this is 90% of the rated I naught.
In the case 2, 90% of the rated input, yeah? Mhm. No, no, that I output, right? The I output is the feed forward signal. The feed forward signal is only like 90% accurate. Like if we know that I output feed forward should be 2.2 ampere, but we are instead feeding only 0.9 into 2.2. This is like we're sort of mimicking a situation where we do not have accurate sensing, or there are, the variation in the sensing, etc. Okay, there's variation in the sensing gains, etc. Then what do we know? We do not have a perfect accurate information of the inductor current. It is just scaled down or scaled up. In this case, we are doing a scaled down version. So even though it's a scaled down version, still it is giving quite a good performance. That's what was the intention of showing this. Now we will just do a comparative study. So this is without load feed forward. This is 90% accurate load feed forward, and this is with perfect load feed forward. So these are the experimental results. So this is also another comparative study. Without load feedforward, with load feedforward, and the operating conditions have changed. The input voltage is 5 volt, the output voltage is 1.8 volt. Okay, these are your PI gains remain the same. So without load feedforward, there's a dip. With load feedforward, the dip is smaller. Okay, these are smaller. So now I'll proceed to explain why we need multi-mode control. So we have studied, so we have understood, like in a previous class, I had told about light load control. Light load control techniques are there, and the popular, and this we had discussed when I taught this constant on-time control. Okay, constant on-time control. It has one advantage that as the load current reduces, your switching frequency also reduces, and hence your switching losses, the loss due to switching, that also will reduce. Okay. So pulse skipping modulation is one thing. So effectively, what is the goal is when the load is this light load, we want to reduce the switching frequency. We want to reduce the switching frequency. That can be brought either by pulse skip modulation. That is, we are either skipping some pulses. So this pulse is skipped. Okay, this pulse is skipped. This is the next pulse. So effective time period becomes 3 into t. Okay, this is your effective time period. So this is pulse skipping modulation is one technique. Another technique is pulse frequency modulation. In that case, we're just increasing the time period. Okay, we are just increasing the time period. So this on time remains fixed, and this time period is increased. Okay, this is another technique known as pulse frequency modulation. So goal is to just change the operating frequency based on the current load requirements. So we want, it is desired. Okay, these are simple requirements that your output voltage should remain more or less fixed at its regulated value, even though your input voltage will change, even though the load disturbance, that is your load increases, decreases, etc., or your load can even vary like this. Still, you want to maintain your output voltage to be fixed at some value. It will not be entirely fixed. When you zoom in, it will be varying. It will be varying some amount like this, etc. But the average value should remain fixed. Okay, and it should not. This ripple should not be too much. Okay, the ripple should not be too much. Okay, it also should have a fast transient performance. In case your load has increased from year to year, it should reach quite fast. It should not like take forever to reach the next steady state operating point. Also, the efficiency should be high, and also we want to reduce the EMI. How much EMI is being generated, we want to reduce that. So at high load, we want to have the frequency to be fixed. It is desired that the frequency remains fixed, and we want to reduce the EMI. Okay. At high load, but at light load, we want to reduce the switching losses, and also we want to maintain the ripple. The ripple delta V output also should be maintained. It should not exceed the limits. It should not exceed the limits. So we want high efficiency with wide input voltage and load current range. So basically we want our converter which will work wherever we put it, in whatever situation, within certain ranges which are specified and which are known to us. It should be able to regulate the output voltage. It should be able to give a good efficiency. It should be able to maintain the ripple constraints, and it should also still give a fast transient performance as well as meet various EMI requirements, etc. So all these things we have to consider, and all these things we have to make sure that it is followed. If we have to do that, then we need to go for multi-mode control. We cannot use only one control technique. We cannot use, okay, we can use one control technique, but we must have different modulation schemes. Okay, or in some cases we can have different control techniques, etc., different gains. All those things are possible. So what happens is we were operating, say, in PWM mode. Then we are transitioning to PFM. Okay, PFM mode. when we are transitioning from one mode to another mode, it should be smooth. It should not just have some sudden abrupt output should not happen because of the transitioning from one mode to another mode. So that is an important requirement. Integrator anti-wind up also is important. When there's an integrator, sometimes integrator can saturate. Okay, it can saturate, and when it saturates, then it takes a long time for your controller to respond. So to avoid that, there is something known as integrator anti-wind up techniques are also there. And we want optimality for all modes is that in any mode of operation, high load, light load, we don't want to use too much of resources. We want to use minimum resources and still get good enough and great functionality from our platform. And also how you give the gate signals, also that is important. So now, if you will observe over here, you will see, suppose we are just operating PWM for the entire range, okay, entire range. This is your conduction loss and this is your switching loss, okay, your switching loss. Your switching loss is fixed because your switching frequency remains the same because you're operating in pulse width modulation. And your conduction loss is this much. So your effective, and this red one is your output power. This is your output. What's your load? That one is your output power. So as your output power is increasing, your efficiency is increasing. Because your efficiency is output upon output plus losses. Okay. So as your output is increasing and your losses, if they are assumed to be more or less same, then your efficiency will increase. So this is shown in pulse width in this graph, okay, with pulse width modulation. But at this low load condition, the efficiency is quite poor. And why is it poor? Because it is mainly due to the switching loss. This switching loss is fixed. Okay, but now in case what we do is this switching loss is increasing as the load is increasing. So what happens is your losses also, they are not fixed. Your losses also are in some sense directly proportional to your output power. Given there's sort of in some sense. So as your output power is increasing, your switching losses also is increasing. But your output power also is increasing. And so your effective losses in comparison to your output power is in a good ratio. And so you get a higher efficiency. So we operate in pulse skipping modulation for low load conditions. And then we transition to pulse width modulation for high load conditions. And that is how we have a high overall efficiency throughout the load range.
Sir, what happens if I use pulse skipping modulation even in the higher load condition?
Okay, if you use pulse skipping modulation in the higher load conditions, there will be higher ripple. Higher ripple will be there. Okay. If there's higher ripple, then those losses will increase. The ripple losses. You know, your inductor DCR, those ripple inductor current would increase. That will increase the losses, etc., etc. This way, those techniques are not preferred for high load conditions. Also, your frequency will vary. Your frequency will change, it will vary. And at light load condition, your effective harmonics and THD will be probably lower at their impact. But in high load conditions, we cannot, their power, your effect at light load, you know, the power present in your harmonics or would be less. Okay, but as you go to high load, that power will increase. So that should not exceed the limits. That's right. Yes, yes.
Sir, in the last year's previous slide, he was talking about that inductor wind up. Right?
Yeah, integrator,
Sorry, integrator wind up.
Yes, yes, yeah.
Sir, in that, you were talking about saturation which means the error accumulation will get saturated. What do you mean, sir?
Saturation means the integrator has some limits, okay, within which it can remain. It has reached some maximum limit. Okay, your controller also has reached the maximum limit. And when your controller is operating at that maximum limit, even though your error is coming, error signal is coming, it is not changing. It is not changing.
Oh.
That's why it has got saturated at that. Now, what will happen is to come out of that saturation, your error must be very large. And so your error, when it becomes very large, then it will slowly it will come out of that saturation. But what happens if your error is very large? What it means is your controller is not operating properly. Okay. So that is why we have to yes, tell them.
Sir, actually, this inductor integrator, when it is operating in PWM, that is in a high load condition, then this problem won't arise. But only if you operate in light load with PWM, this problem is arising.
No. This is integrated problem is a problem of control. It's a problem of control problem. It can occur even in PWM. It can occur in any case.
Because it is written under need for multimode.
No, not for that case. It is the challenges in multimode control. What happens is when we are moving from PWM to PSM. Okay, in that case, we must take into account the history term of the integrator. The past history of the integrator. We must note that down and we must continue. So, like what is happening is there could be a bump. There could be a sudden change in your control output because you're changing from PWM to PSM. Okay, if there's a sudden bump, what will happen? Your output also will have some sudden change. Your output also will have some sudden change. That is not desirable. Okay, so that's why there's something called a smooth controller transition that we try to take care. That we will explain in the next week. Let's see for 1 minute. And in case there's and in certain cases, in case the integrator gets saturated, then we have to have an anti-wind up arrangement also is there. And if you normally also we will keep certain saturation limits that we don't want the duty ratio to exceed certain limits, etc. We have certain protection in our code already written, which we have. Okay. And Banerjee was saying, 1 minute. Can we say in PSM switching losses increases with load and decreases with load? Yeah, so switching losses will increase with load in PSM and it will also reduce as the load is reducing.
Sir, in the slide, what is this change, sir? In the first diagram, there is no change in the blue color, whereas in the second diagram, there is a change.
It should not be there actually. The change should not be there. Because if you assume that to be static losses, then that should remain the same throughout. Okay.
Okay.
See, these are just conceptual figures. Okay, they're not the actual figures. So these are just for you to understand the concept of the need for multimode control.
Okay. Sir, sir, in the constant on time more block diagrams we saw in the last week, right? Sir, if for the counter, if the input to the reset is not 0, it is not 1, what it gonna do, sir? How it gonna respond? Sir, in the block diagrams we talked in the last week, the constant on time block.
Okay.
Sir, if the input to the reset, there is a reset for the counter. If the reset is non-zero, how can we judge the state of the counter, sir? What output it gonna have?
No, if the counter is, the reset is non-zero, if the reset is non-zero, reset is 1, then the counter will go to 0. No? If the reset becomes 1, the counter will go to 0.
If the reset is not equal to 1.
If it is not equal to 1, then the counter will either have the previous state, or when the clock comes, it will get incremented.
Okay, sir.
Okay, so we can implement digital voltage mode control in the buck converter. Okay, this is the logic, FPGA code. Similarly, you can implement digital pulse skipping modulation. Okay, so this same similar block diagram is there. What we want to do in multi-mode control, we have PSM logic and digital pulse width modulation. Both those logics we consider. So we are having the output for digital voltage mode control we are giving, as well as the output for digital pulse skipping modulation. Both are generating certain gate signals. But which gate signal we will choose depends upon this PWM/PSM select line. Okay, this select line will determine if we are taking PWM or PSM. So suppose the select line is 0, that means we are taking PWM. So the high side you will get QH temp, and on the low side you will get QL temp. But in case it was 1, then at the high side you will get this QH temp 1, and at the low side you will get a value 0. Because why 0? Because we are assuming it is operating discontinued mode, as it is light load condition. Okay, light load condition.
But I didn't get the point here.
Okay, no. In your controller, you're implementing voltage mode control, digital voltage mode control, as well as digital pulse skipping modulation. Both are being concurrently being processed, and both are generating gate signals. Okay, but which gate signal we will choose effectively to send to our buck converter, that depends on the value which we assign to the select line. Okay, so if we are operating in high load condition, high load means we must operate in PWM. Okay, so we will give the value 0. When we realize it is gone into light load, then we have to go to PSM, at which we have to give the value 1. Okay, and effectively the gate signals change accordingly.
Sir, here the top block PWM block is generating 2 outputs, whereas the PSM is generating only 1 output. That is my doubt, actually.
Yeah, because the one output is 0, no? The one output is 0 because it is light load condition. No? So the buck converter, if you remember, buck converter, you have one MOSFET here, another MOSFET over here, right? And there's a diode over here. If this is, sorry, if this is 0, then only diode will conduct. And then it will operate in DC only. Okay, that is for light load condition, we do that. Okay. So similarly, there's one question like which you guys can solve about how the loop shaping we can do. Okay, like what I had shown now, you can use pole zero cancellation. You can select the crossover frequency, and then you can find out what is the phase margin you are obtaining. But you must consider some delay. You have to consider. You have to consider some delay. We'll have to assume some delay is around T by 1000. Assume. Okay. So using that, you can get what would be the phase margin. Okay. So are there any other questions? Any other doubts? Hello.
Yeah, good. No,
Okay, Shankar, do you have any queries? So, Shankar, where are you working or studying? Because I know about the other two guys. I don't know about you. Okay, and one more thing, I'll be having the next session next week for week 12, and then there will be a sort of recap session on Thursday. Okay, Thursday between 6 to 7. There will be a recap session. Okay, not this Thursday, next Thursday, after 10 days.
that, sir, that we'll be receiving the mail from NPTEL, right?
Yeah, you'll be receiving the mail. They should, they already told them, they should schedule and send you the mail. Okay, then. If there are no other queries, okay, let's say something, Rajasekhar.
Thank you, sir.
No, sir. No. Good, sir. Good night, sir. Thank
Okay,
you.
good night. Okay, thank you. Bye.